Welcome back to Math 104. Our task is to find the probability that a randomly selected student is not a history major who lives on campus. Here the phrasing requires a bit of interpretation. It's a bit more natural to read this as if it were hyphenated this way. Not a history major who lives on campus. That is, not a campus-dwelling history major. You might be tempted to think that it's asking about a non-history major, that is, someone who's majoring in not history, who lives on campus. That's a less natural reading, and if it meant a non-history major who happens to live on campus, it would have been phrased differently, as not a history major, but lives on campus. This is a little bit subtle, but interpreting English phrasing, or phrasing in any other language, is part of applying probability to real life. So we are asked to find the probability of the following event not being a campus-dwelling history major. Well, how many campus-dwelling history majors are there? There are 50 of them, and they live right here in these two basic regions. So this probability is 1 minus 50 out of 1,000, which is 950 out of 1,000, or 0.95. If we weren't sure, we could start with drawing a Venn diagram and shading everywhere that you find someone who is not simultaneously in the H circle and in the C circle. So we're doing all this shading in all 6 of these regions outside of H and outside of C. If we wanted, we could count up all the numbers in those 6 shaded regions. They add up to 950, or perhaps this shading just makes it clearer that we want everyone except those 50 students to count towards the event. Our next question is to find the probability that a randomly selected student is a junior who lives off campus and is not majoring in history. Again, we need to do a little bit of interpretation. I claim that the way the word who is used here is essentially the same as and. So we're asked for the probability that a randomly selected is a junior and lives off campus and is not majoring in history. Let's think where this event lives in the Venn diagram. So inside the J circle is a junior, lives off campus, so in the J circle, outside the C circle, and is not majoring in history. So this student is one of the 70 who is inside the J circle, outside the C circle, and also outside the H circle. So we're looking here for the probability of J intersect C complement intersect H complement. Sure enough, it turns out that a single basic region in a 3-circle Venn diagram is a 3-way intersection involving J, C, and H or their complements. There are 70 students who live in this category out of 1,000. That gives us a 0.07 probability. In the Venn diagrams we have looked at thus far, we have had examples with many outcomes in a single basic region, or sometimes just one outcome in a basic region, and occasionally no outcomes at all in a basic region. Something interesting happens in this next example. In the experiment of flipping a coin 3 times, let's look at the events H1, H2, and H3. H1 is the event that the first coin shows heads, that is, the first flip of the coin shows heads, H2 the event that the second coin shows heads, and H3 the event that the third coin shows heads. Let's see what happens when we write each outcome of this experiment, that means 3-letter words consisting of H's and T's, into its appropriate region of the Venn diagram. It's a good exercise if you want to pause the video right now and try to do it yourself before I go through the details. When in doubt, start in the middle and work your way out. The only outcome inside all 3 events is heads, heads, heads. Heads on the first gets you inside the H1 circle, heads on the second flip gets you inside the H2 circle, heads on the third flip gets you inside the H3 circle. How about this region here? What could possibly live in this region here? It's inside the H1 circle, it's also inside the H2 circle, but it's outside the H3 circle. Notice how going through step by step and identifying where the region lives with respect to H1 determines what I write for the first letter. Looking at where the region lives with respect to H2 determines how I write the second letter, and looking where the region lives with respect to H3 tells me how I have to write the third letter. Here we started out looking at the region, noticed that it was outside the H3 circle. That forced the last letter in the word to be a T. So there is only one word, there is only one outcome living inside this basic region. Over here we've got tails, heads, heads. That's the only way to be outside of H1, but inside H2 and inside H3. Over here we've got heads, tails, heads. That's the only way to be inside H1, outside H2, and inside H3. Right here we've got heads, tails, tails. That's the only way to be inside H1, outside H2, and outside H3. Similarly, tails, heads, tails, 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 heads, and finally, to be outside all three circles means tails, tails, tails. Aha! Each outcome of the experiment corresponds to one and only one basic region of the Venn diagram. In a certain sense, working with these three events, and therefore these three circles, completely sorts out what is really going on inside the experiment. It also shows that the number of outcomes in the experiment is exactly equal to the number of basic regions in the Venn diagram. If we hadn't already known that there were 8 basic regions in a 3-circle Venn diagram, this would have demonstrated it for us. 8 outcomes in the experiment, 8 basic regions in the diagram. Let's take a closer look at what we just did. Each basic region in the Venn diagram corresponds uniquely to a set of answers to the following 3 yes or no questions. Is the region inside the H1 circle, yes or no? Is it inside the H2 circle, yes or no? Is it inside the H3 circle, yes or no? The answers to those 3 questions uniquely determine each basic region. So identifying a particular basic region is a 3-stage process with 2 possibilities at each stage. In exactly the same way, forming an outcome of the 3 coin flip experiment is a 3-stage process with 2 possibilities at each stage. This is why we represent the outcomes as 3-letter words with 1 letter for each stage in an alphabet with 2 available letters. Why 2 available letters? Because there are 2 possibilities at each stage. There are many experiments in which the outcomes can be described as words, n letters long, based on a 2-letter alphabet. That's the case whenever the experiment is an n-stage process where every stage has 2 possibilities. Examples we've seen include flipping a coin n times and observing the sequence of heads and tails, so we write the outcomes as n-letter words consisting of H's and T's. Another is randomly selecting a family with n children. We've talked a lot about that one. And observing the birth order of boys and girls. There we write outcomes as n-letter words, words that are n letters long, consisting of B's and G's. If there are n children, and they are born one at a time, there are n stages in the process, and each stage has 2 possibilities. Here are the experiments. Guessing the answers to a true-false test with 5 questions. Guessing the answers to a multiple choice test with 2 questions, but 5 possible answers to each question. Rolling a 6-sided die 5 times. And finally, surveying 5 people in a row and asking them their preferred candidate for president.